All right, last two examples for geometric distributions. Example number 6 says, what is the probability of first tossing a head in fewer than 3 tosses? Now that's a little different. Fewer than 3 means, could we have first tossed a head on the first toss? Sure. Could we have first tossed a head on the second toss? Is that fewer than 3? Yes. What about first tossing head on the third toss? Is that fewer than 3? No, we can't do it that way because that's not fewer than 3. So what this means is that it could have happened on the first toss or the second toss only. You cannot toss a coin 3 times and have the first head happen in fewer than 3 tosses. Okay, so that's important because if it could have happened on the first or it could have happened on the second, or meaning cases, then we know that the probability of x equaling either 0 or x equaling 1 should be the answer to this question. When I say the probability of x equals 0, what do I really mean? I mean that there was 0 waiting time. So the probability of x equals 0 is actually calculating this, getting ahead on the first toss. And the probability of x equals 1 means, well, you guessed it, we had 1 trial that we had to wait through or fail. And if there was 1 failure, then this first tossing ahead must have occurred on the second toss. So these are the two probabilities we need to calculate. We're tossing ahead, so failure is 1 and 2, success is 1 and 2. If we're trying to find the probability that x equals 0, then half must have happened 0 times a half. That's the probability of flipping ahead. Plus, if I failed once, then that means I must have flipped a tail once. That's a failure raised to the 1 times ahead. This is 0.5. This is 0.25. And so the answer is 0.75. There must be a 75% chance of first tossing ahead in fewer than 3 tosses, is the answer to that question. Okay, let's go on to example 7, the last example for this topic. And let's just figure out the difference between these questions. First, what is the probability that you will first cut an ace? Cutting, remember, in a deck of cards is cutting and showing it and then replacing it. What is the probability that you'll first cut an ace on the 5th cut? So, did it happen on the first cut? No, no ace. Second, no. Third, fourth, no. 5th cut, yes. So when we're calculating this, we're only calculating the probability of waiting how many times? That's right, 4 times, because it happened on the 5th cut. So if we're waiting 4 times, that means we need the probability of failure. What's the probability of not cutting an ace? Well, there's a 4 in 52 chance of cutting one. There must be a 48 in 52 chance of not cutting an ace. Raised to the, how many times did we fail? 4 times? Right. And then finally on the 5th try, we actually got it. There's a 4 in 52 chance of cutting an ace on the 5th try. Altogether, that answer is 0.0558 or a 5.58% chance of that happening. Now, how is this different than B? B, it says on the 5th cut. So we're talking about a specific probability. Or sorry, A. A is talking about a specific probability. In B, it says in fewer than 4 cuts. So when could this first cut of an ace happen? It could have happened on the first cut. Could have happened on the second cut. Yeah, that's definitely fewer than 4. It could have even happened on the 3rd cut. Could have happened on the 4th cut? No, that's not fewer than 4 cuts. So we have cases here. and we have to calculate each case independently. If this happened on the first cut, then we have a 48 in 52 chance. That did not happen, no failures, raised to the 0 times 4 in 52. On the second cut, that means we failed once, so 48 in 52, that's my failure probability, raised to the 1 over 4 in 52. And on the third cut, that means we must have failed twice. 48 in 52 squared times 4 in 52. And what do we do with all of those cases? We add them up. I'll let you figure that part out in fewer than 4 cuts. And part C, what is the expected waiting time before you cut an ace? Well, now that's talking about the expected or on average waiting time. Well, let's think about that. If we're cutting an ace, we know that that's a 4 in 52 chance of that happening, a 48 in 52 chance that it does not happen, and so the expected waiting time here is 48 in 52 divided by 4 in 52, which is 48 divided by 4, which is 12. And that makes perfect sense. The expected waiting time is 12 cuts before you cut the first ace. Remember, there's a 1 in 13 chance of cutting an ace. So by waiting 12 times, on average, we should see our first ace. It might not happen that way. It might come up sooner than that. But on average, we should have to wait about 12 times before we cut our first ace. Okay, that ends geometric distributions. Good luck on your homework. I will post it on the classroom as usual. Please keep your eyes open for the next lesson, 6.4, hypergeometric distributions. That'll come up very shortly, I'm sure.